In today's lecture, I will navigate you through the second part of sample ionization techniques. You will learn the principle and components of electrospray ionization, inductively coupled plasma, secondary ion mass spectrometry, fast atom bombardment, and matrix-assisted laser desorption or ionization. Electrospray ionization (ESI) is the most prominent technique among the group of atmospheric pressure ionization methods. Electrospray ionization is a soft ionization technique that is typically used to determine the molecular weights of proteins, peptides, and other biological macromolecules. ESI is extremely useful for the analysis of large, non-volatile, chargeable molecules because this process does not fragment the macromolecules into smaller charged particles. Rather, it turns the macromolecules being ionized into small droplets. These droplets will then be further dissolved into even smaller droplets, which creates molecules with attached protons. These protonated and dissolved molecular ions will then be passed through the mass analyzer to the detector, and the mass of the sample can be determined. In ESI, the solution is composed of a volatile solvent containing the ionic analyte at very low concentrations. The transfer of ions from the condensed phase into the state of isolated gas phase ions starts at atmospheric pressure and incrementally proceeds into the high vacuum of the mass analyzer. The formation of multiple charge ions follows out the mass-to-charge scale by the number of charges, which shifts the ions into a mass-to-charge range accessible by most mass analyzers. Most high mass analytes examined by ESI readily form multiply charge ions. Normally, it is therefore sufficient in ESI mass to cover the range up to mass to charge ratio 3000 for the detection of ions. This does not preclude, however, that ESI can produce ions of much higher mass to charge ratio. Even ions at mass to charge ratio of 85,000 has been observed. A brief summary of ESI processes. ESI is a soft ionization technique that causes minimal fragmentations of large and thermally unstable molecules, which enables multiple charges having linear relationship between the average charge and molecule weight and can easily couple with HPLC. Next, let's look into the underlying mechanisms of electrospray ionization, including four critical steps: liquid charging, droplet formation, droplet evaporation, and ion emission from the liquid. Two main processes are proposed to explain the ion transfer process in the gas phase: ion evaporation mechanism, or IEM, where the electric field of the surface of highly charged small droplets becomes sufficient to desorb ions directly from the surface. In this process, solvated ions leave the larger droplet, and subsequently the droplet shrinks until dissolved ions remain. The second is the charge residue module (CRM), where ions eventually become desolvated as solvent molecules leave the droplet surface. In this process, solvent molecules evaporate from the larger droplet and the droplet shrink until just dissolved ions remain. Evidence suggests that smaller ions are more likely to enter the gas phase by the IEM, whereas the larger multiple charge species are more likely to follow the CRN. The voltage difference between the emitters and counter-electron establish an electric field, typically million volts per meter, pushing the charged ions moving towards the mass analyzers. This diagram illustrates the setup of electric fields in positive ion mode, where the spraying nozzle will be applied 2000 volt to 5000 volt to positively charge the liquid droplets. The counter electrode or glass capillary would have the negative 2000 to negative 5000 volt to direct the ion flow. The electric field between the spraying nozzle or emitter and the counter electrode is important for the ESI ionization efficiency. The electric fields can be described by the applied voltage, the inner diameter of spraying nozzle, and the distance between the spraying nozzle and the counter electrode. The accumulated charges, positive or negative, will be repelled by the high voltage capillary of the same polarity, and then they would drift towards the liquid surface at the capillary outlet. However, the accumulated light charges at the surface are destabilized, and finally the meniscus will be drawn out and deformed into a cone under the influence of a very high electric field. This cone is called the Tyler cone, after the name of the scientist Tyler, who first theoretically described the conditions under which a stable liquid cone can exist with the competing forces of an electric field and the surface tension of the liquid. This Tyler cone is a zone of high turbulence. At high field strength, it immediately starts ejecting a fine jet of liquid from its apex towards the counter-electrode or heated capillary. This charged jet easily breaks up into small droplets. The droplets produced at low flow rate, or typically 5 microliter per minute, have a narrow distribution of sizes with a most abundant radius about 1.5 micrometer. Such an electrospray droplet was shown to have a charge of 10 minus 14 order of minus 14 coulombs, which corresponds to 60,000 singly charged ions. All those charged droplets are driven away from each other by Coulombic repulsion and move along the direction of the electric fields towards the heated capillary. Overall, under positive ion mode, a positive charge aerosol is formed, and in negative ion mode, negatively charged aerosol is formed. The positive charges are mostly contributed by protons, and negative charge are contributed by some negative ions. The cone instability is profoundly influenced by the surface tension R of the fluid. Therefore, the onset voltage required to initiate the charge droplet emission can be described by surface tension of the fluid, the inner diameter of spraying nozzle, and the distance between the spraying nozzle and capillary transfer tube. The larger the surface tension and the greater the distance, we will need a higher onset voltage to initiate the charged droplet emission. Therefore, onset voltage is higher for liquids with higher surface tension. For example, water has a higher surface tension and those requiring about twofold onset voltage compared with methanol. You may ponder that we can just apply a high voltage to initiate a charge droplet emission of all kinds of solvents, right? However, the higher voltage will increase the probability of electrical discharge, especially in negative ion mode. Decreasing pressure can increase the chance of corona discharge, and this is why ESI is done at ambient pressure. Okay, now the droplets are successfully formed from the Tyler cone. The droplet size will affect the ionization efficiency. The radius of an electrosprayed droplet R depends upon the fluid density, though, flow rate (Vf), and surface tension. Higher flow rate results in larger initial droplet sizes. Larger droplet sizes lead to lower ionization efficiency because the droplets are not so close in size to the Rayleigh limit. To achieve the higher ionization efficiency, a nebulizer gas or sheath gas is usually applied to reduce the surface tension of the solvent at higher flow rate. So what is the Rayleigh limit? In 1882, Lord Rayleigh theoretically estimated the maximum amount of charge a liquid droplet could carry before throwing out fine jets of liquid. This is now known as the Rayleigh limit. When charge Q becomes sufficient to overcome the surface tension which holds the droplets together, Coulombic explosion or fusion begins. The larger the surface tension or the radius of the droplet, the higher the Rayleigh limit. Now that the charged droplets have been released from the spraying nozzle, they are accelerated towards the counter-electrode. Shrinkage of the droplets results as a combination of two factors: a solvent evaporation and droplet disintegration by Coulombic explosions. Miniaturization of electrospray or nano electrospray is even more attractive than access to high liquid flows for better ionization efficiency. The tip has a narrow bore axis of 1 to 4 micrometer diameter, making flow rates of 20 to 50 nanoliter per minute sufficient to provide a stable electrospray. Nano ESI allows for high polarity solvents such as pure water in both positive and negative ion mode, has extremely low sample consumption, and tolerates even higher loads with the buffer salts than conventional ESI. Nano ESI usually uses disposable capillary, therefore is free of the carryover effect. As the nano ESI generates a smaller droplet, the Rayleigh limit is smaller in nano ESI, which means that it is easier to initiate ionization with nano ESI. The spray voltage would have a profound effect on the shape of nano electrospray pumps. From low, about 950 volt, to high voltage around 2200 volt, the nano electrospray pumps can form dripping, a spindle, or a cone jet, or a pulse cone jet or multi-jet. Only pure cone jet will deliver stable electrospray for the analytical work. The most commonly applied flow range is the intermediate flow range from 1 microliter to 200 microliter per minute, using HPLC columns with 1 or 2.1 inner diameter, which provides both high sensitivity and a decent column loading. In this particular flow range, sensitivity of ppb to ppt can be expected. When using a higher flow rate, droplet evaporation rates would limit the ionization efficiency and sensitivity. The additional heating process will enhance the evaporation rates and thus increase the ionization efficiency. The extra heat can be supplied in three places: the drying gas, the transfer capillary, and the atmospheric region. As evaporation is endothermic, heating to several hundred degrees usually do not lead to severe thermal degradation. In addition, the solvent composition and analyte polarity can affect the extent of the ionization gain from the heating process. For example, high aqueous solvents benefit more with heat than high organic solvent. The analytical detectors can be classified into two major classes: the concentration-sensitive detectors or mass-sensitive detectors. For concentration-sensitive detectors, the detector response is a function of the concentration of analyte in the mobile phase. Therefore, a smaller column internal diameter can bring a higher sensitivity because a more concentrated plug eluded. The concentration increases as an inverse function of the square of the column diameter. For mass-sensitive detectors, the response is a function of the absolute mass of analyte passing through it. There is no sensitivity gains with smaller columns or flows. ESI is fundamentally mass-sensitive. The apparent concentration-sensitive response is the result of the balance between the ionization efficiency and mass flux into the electrospray needle. Ionization efficiency remains constant at different flows, but the fraction of the available ions passing through the orifice at the atmospheric to vacuum interface is increasing as the flow is lowered. The smaller columns means a higher absolute sensitivity, and the lower flows means longer acquisition times on a given amount of sample. Therefore, the post-column stream splitting do not result in a significant signal loss. This figure illustrates that splitting the column flow can even enhance the signal intensity. Panel A only directs 15 microliter per minute to source, and panel B directs 132 microliter per minute to source. Despite panel C directs all flow, like 400 microliter per minute into the mass, it has the lowest number of peak area. Electrospray ionization can be operated in positive or negative ion mode. The analysis in each ion mode will have the optimal performance in solution of favored pH value. For example, acidic compounds can easily form negative charge species under neutral to slightly basic solution conditions, and those observed best in the negative ion mode. On the other hand, basic compounds can easily generate positive charge species in acid solution, and those observed best in the positive ion mode. For polar neutral species, addition of ammonium acetate can induce the formation of ammonium added ions, and those facilitate the ionization. The inductively coupled plasma, ICP, is an ionization source that fully decomposes a sample into its constituent elements and transforms those elements into ions. It is typically composed of argon gas, and energy is coupled to it using an induction coil to form the plasma. The ICP device consists of the quartz tube, the end of which is wrapped in a high-power radio frequency induction coil. Argon gas flows down the quartz tubes at a high rate. A current of electricity is run through the RF coil, which produces a magnetic field inside the end of the quartz tube. Sparking the argon creates some argon ions, which are now paramagnetic and absorb energy from the magnetic field. The argon ions absorb enough energy that a plasma is created in the area of the tube covered by the RF induction coil. The nature of the magnetic fields causes the plasma to flow in a closed annular path, basically a donut shape. What is especially impressive is that enough energy is absorbed from the magnetic field to heat the plasma up to a temperature of about 6000 K. As a comparison, this temperature is about the same as the temperature of the surface of the sun. The hot temperature means that new argon flowing into the plasma is ionized, which maintains the plasma. The plasma is kept from melting the walls of the quartz tubes by an additional tangential flow of argon along the walls of the tube. Finally, the sample is nebulized and sprayed as an aerosol mist into the center of plasma. An ICP offers several advantages over flame and furnace atomization sources. One is that it is so hot that it leads to a more complete atomization and leads to the formation of many excited state atoms. A second advantage of an ICP is that all of the elements can be measured simultaneously. All metals in the sample will be atomized at the same time, and all are emitting light. The inductively coupled plasma tends to be quite stable and reproducible. The combination of high temperature with chemically inert environmental reduces the matrix effect in the plasma relative to other atomization sources, but it does not eliminate them, and matrix effect must always be considered. Lastly, there are now methods to introduce the atoms generated by ICP into a mass spectrometer. The use of mass spectrometer may further reduce certain matrix effects. Also, mass spectrometry usually provides more sensitive detection than emission spectroscopy. In the following slides, we will go through the common desorption or ionization methods that uses the impact of energetic particles, including the secondary ion mass spectrometry, plasma desorption, molecular beam solid analysis, fast atom bombardment, and massive cluster impact. Plasma desorption ionization mass spectrometry, PDMS, also called fission fragment ionization, is a mass spectrometry technique in which ionization of material in a solid sample by bombarding it with ionic or neutral atoms formed as a result of the nuclear fission of a suitable nuclide, typically the Californian isotope. Based on how it was used, PDMS is rather the precursor of matrix-assisted laser desorption or ionization (MALDI), based on the principle of ion generation. It is closer to secondary ion mass spectrometry and fast atom bombardment. In Californian PDMS, particles of mega electron volt translational energy are created from radioactive decays of Californian nuclides, the nuclear process being the source of their kinetic energy. Each event yields two nuclides of varying identity, the sum of their masses being the mass of the former nucleus. The fission fragments of similar mass are traveling in the opposite directions. Thus, only one of each pair can be employed to affect desorption of ions from the same film of analytes on the supportive foil. The ionization process in Californian PD is different from fast atom bombardment with some closer relations to dry secondary ion mass spectrometry. Molecular beam solid analysis is the first technique to use a beam of energetic neutrals, usually argon or krypton, to achieve sputtering and ionization of solid samples. The noble gas was first ionized in the primary ion source. The ions were accelerated by a high voltage of several kilovolt and then neutralized by transmitting the primary ion beam through a charge transfer cell with the neutral gas of the same species. The neutral beam then hit the analyte material on the target in the analytical ion source, where analyte got ablated and becoming ionized. Here are some examples for molecular beam solid analysis. MBSA can be applied to analyze inorganic or organic compounds. In secondary ion mass spectrometry, a primary high-energy beams of ions, usually oxygen, argon, or cesium, with energies of about 10 kilo electron volt, is aimed at a small area of the sample, such as a mineral grain. Next, the primary ions sputter away the sample by causing the ejection of atoms and ions called the secondary neutrals and ions. These secondary ions, approximately 1% of the sputtered material, are accelerated into a mass spectrometer to reveal the elemental and isotopic characteristic of the sample. Fast atom bombardment is an ionization technique established in 1981, which is widely used as an ion source in mass spectrometry systems. Unlike other ionization techniques, FAB bombards a sample with a neutral atom to ionize the sample. The use of neutral atoms avoids the accumulation of charge in the insulating sample and facilitates ionization of the sample. The sample itself is usually mixed with a non-volatile chemical protection environment called matrix. The analyte should be soluble in the matrix. Otherwise, addition of co-solvents like dimethylformamide (DMF) or dimethyl sulfoxide (DMSO) or other additives can become necessary. Only low vapor pressure solvents can be easily used as a matrix in FAB. The viscosity of the solvent must be low enough to ensure the diffusion of the solutes to the surface. In addition, ions from the matrix itself should be as unobtrusive as possible in the resulting FAB spectrum. The matrix itself has to be chemically inert. However, specific ion formation reactions promoting the secondary ions yield more advantages. The FAB gas is introduced via a needle valve into a lower part of FAB gun, mounted above the ion source. Neutralization of the energetic noble gas ions is affected by a charge transfer with incoming neutrals. The kinetic energy of the atoms is mostly conserved during the charge transfer, and thus the neutrals heat the exposed surface with high kinetic energy. FAB is very effective for the analysis of non-volatile, thermally unstable polar compounds. The ionization products N plus hydrogen or N minus hydrogens are produced in pairs in FAB, facilitating the analysis of positive ion mass spectrometry and negative ion mass spectrometry. The FAB has high sensitivity and consumes that sample. The minimum measured molecule weight of the sample can be several, like 10 to order of negative 9 gram, and the utilization rate of the sample is high. For biologically active substances, the residual sample remains active and can be recycled due to the bombardment of the neutral particles used. In addition, the ionization probability and detection sensitivity of each component in the sample are related to the sample composition. If the energy required for ionization of one component is lower than the other components in the sample, the ionization probability of the components is large. However, FAB is not suitable for separating samples. It is difficult for FAB to separate the sample with low affinity proton abilities from samples with high affinity proton abilities. Moreover, for samples of mixtures of different volatility, FAB cannot fractionate and ionize the components. Massive cluster impact (MCI) mass spectrometry presents an additional means of generating secondary ions by bombardment of a surface. The massive clusters of up to 10 of order U are generated by electrohydrodynamic ionization of an electrolyte or glycerol solution. For example, 0.75 molar ammonia acetate in glycerol. The resulting clusters, consisting of about a million glycerol molecules and bearing about 200 electron charges on the average, are accelerated by a 10 to 20 kilovolt high voltage. Massive cluster impact is suitable for analysis of molecules with high mass, which can analyze proteins up to 17,000 U. Laser desorption or ionization was firstly introduced in the late 1960s, which is suitable for low mass organic salts and light absorbing organic molecules, but difficult to analyze the high mass molecules like over 2000 U. Matrix assisted laser desorption or ionization (MALDI) is a technique for soft ionization of mass spectrometry that uses a laser energy absorbing matrix to create ions from large molecules with minimal fragmentation. It has been widely used to measure the molecular weight of biomacromolecules such as peptides, proteins, nucleic acid, molecular weight distribution of polymers, and oligomer analysis. MALDI's mass spectrometry is characterized by high sensitivity, wide application range, and simple operation. It has extended the traditional mass spectrometry technology, meaning for small molecule research to analyze a range of highly polar, hardly volatile, and thermally unstable samples. The MALDI method is divided into three steps. First, the sample is mixed with the appropriate substrate material and applied to the metal plate. Secondly, the pulse laser irradiates the samples, triggering the ablation and desorption of samples and matrix materials. Finally, the analyte molecules are ionized by protonation and deprotonation in the hot plumb of the ablation gas, and then accelerated to the mass analyzer to analyze them. For heat-sensitive compounds, if they are heated very quickly, they can be prevented from being thermally decomposed. The MALDI technique is similar to this principle in a tiny region in a very short time interval on the order of nanosecond. The laser provides high-intensity pulse energy to the analyte on the target, allowing it to desorb and ionize in an instant without producing thermal decomposition. MALDI is a mass spectrometry ionization method for directly vaporizing and ionizing non-volatile samples, but its ionization mechanism is still unclear. There are two possibilities that ions are formed in a solid state, and the laser irradiation is only a simple release or produced by a laser-induced ion molecule reaction. The two major parts of LDI and MALDI are the laser pulse or energy source and sample layer. The short pulse laser supplies energy onto the sample layer. Usually, the laser beams focus to spot sizes of 50 to 500 millimeter diameter. The energy deposit can be determined by three factors: laser irradiance, pulse width, and sample absorption. The solid sample layer absorbs energy from laser pulse, causing evaporation and eventually ionization of the sample. This whole process is generally operated at ambient temperature. The wavelength lambda determines the photon energy carried by the laser pulses. For a laser with wavelength of 355 nanometer, we can calculate the energy it carries is 3.49 electron volt. A single photon will not be able to cause ionization. Instead, MALDI relies on the coincidence of a large number of photon absorptions across a macroscopic area. Therefore, short pulses are needed to induce a sudden ablation of the sample layer. An extremely short time interval of ion generation basically avoids thermal degradation of the analyte, also means a better definition of the starting pulse, which is relevant when a TOF analyzer is being used. This table illustrates the commonly used lasers for laser desorption ionization. The UV laser sources usually supply greater photon energy compared with the IR lasers. The highlighted ones are the most frequently used UV lasers. Let's review some basics regarding to the ion yield and laser fluence. Fluence is defined as energy per unit area. In MALDI, this value typically falls into the range of 10 to 100 millijoule per centimeter square. Irradiance is fluence divided by the laser pulse duration, where MALDI typically has a irradiance in the range of 1 to 10 million watts per centimeter square. As a rule of thumb, the ion formation does not occur below a laser irradiance threshold of about 1 million watts per centimeter square. At threshold, a sharp onset of desorption or ionization occurs and ion abundance is raised to a high power of laser irradiance. The threshold laser fluence for the detection of matrix and analyte ions not only depends on the actual matrix, but also on the molar matrix to analyte ratio. This figure illustrates the effect of molar matrix to protein ratio on the threshold fluence. If we take cytochrome C as an example, the optimal molar matrix to protein ratio is 4,000 to 1. At this specific ratio, we need the minimum energy to induce the ionization. If we use a concentrated 100 to 1 or less concentrated million to 1 molar matrix to protein ratio, we may require almost a double energy to induce the ionization. The choice of matrix is one of the most important steps in MALDI analysis. The ideal matrix generally has the following properties: strong electron absorption at the laser wavelength used, better vacuum stability, lower vapor pressure, good miscibility with the analyte in the solid state. In MALDI technology, the matrix has a spatial effect on the analysis of the sample. Dilute the sample to dissociate the clustered macromolecule. Protect the sample. The matrix absorbs the laser energy and then transfers it to the sample to avoid direct laser irradiation of the sample and lead to decomposition of the sample molecules. The choice of matrix depends primarily on the wavelength of the laser used, followed by the nature of the object being analyzed. Commonly used substrates are niacin, 2,5-dihydroxy benzoic acid, and methonic acid. Most MALDIs use solid or crystalline organic matrices, but these matrices produce corresponding background peaks in low mass regions, which interfere with the characterization of small molecule compounds. Recently, a series of new matrix materials has been reported which can reduce or remove the matrix interference, such as high molecular weight porphyrins, surfactant inhibiting substrates, inorganic materials, carbon nanotubes, and porous silicone. In addition, the addition of matrix additives to the matrix solution can improve the analytical results and greatly improve the sensitivity, reproducibility, resolution, and signal suppression of desorption. Compared with other mass spectrometry ionization techniques such as electron bombardment ionization and chemical ionization, MALDI technology has the following characteristics. First, it can ionize some samples that are difficult to ionize by other ionization techniques, especially biomacromolecules, and obtain complete ionization products without obvious fragments. It has a dominant single-charge molecular ion peak and simple mass spectrum, which is suitable for analysis of multi-component samples. The requirements for sample processing are not strict, and even untreated can be directly analyzed. MALDI can be coupled to Fourier transformed ion cyclotron resonance mass spectrometry (FTICR) mass, and its resolution is further improved. To sum up, the ionization efficiency of MALDI is highly sensitive to sample preparation, where matrix, solvent system, substrate material, sample purification, and sample crystallization can all play important roles in MALDI. In addition, MALDI imaging can be an art form that visualizes the distribution of chemical or metabolite in the tissues or biological samples, which provides invaluable spatial information. Here are some useful reads if you'd like to explore more. And that's for today. Good luck.